Alright, so welcome back. We're going to continue this tutorial, and now that we've made the simple particle system and visualized it, we're gonna move on to making the synth part, controlling the sound with it. And like I said in the last video, it's just going to be an oscillator bank, one oscillator per particle, and sorry, one oscillator per particle, and the X position left to right of each particle is going to change the panning, and the Y position up to down is going to change a wavefolding. 0, no wavefolding, 1, full wavefolding. And as you can see, maybe these things go off the screen a little bit before they hit the edge. The reason I think is because of the perspective. I'm not very good at dealing with these perspective things in OpenGL. So there's probably a better way to do this. Maybe change it to ortho or something. But just to be really lazy, I'm just going to scale this down a little bit, maybe to... So it's going to be 20 times. I'm just going to scale it down to 8.8. Maybe 8.2 is good. Or 8.3. Yeah, so I think you should just change the perspective or adjust the Z. And you can do that instead of even scaling this, probably. You can probably just translate the view of this. But this is just another way to do it. Okay, great. So let's go and code the synth. So we're going to go back. I'm going to delete this. We're going to go back into the gen. So here's where we ran our simulation, and we ran it at this frame rate of 500 samples. So every 500 samples, it changes these, and that's even really fast. You don't even have to run particle systems that fast. You can kind of decide on that, but just keep in mind that the frame rate and velocity together are affecting kind of how quickly these move, both in different ways, but they affect the same thing essentially. So yeah, now down here we're going to add the DSP for the oscillators, and this will run at audio rate, so none of this frame rate stuff. And so yeah, similar to the simulation, we're going to go through each particle. So I'm just going to copy the loop. So we're just going to loop through each particle. And like I said, we're going to create oscillators. Now you can't just do something like signal equals cycle of frequency because this is a loop. So if this wasn't in a loop, like if you did this part in a poly, you won't need to do any of the shenanigans I'm about to do, which could be a good workflow. You know, you could do in-gen this whole simulation like this, but then not do the DSP here and instead do it with like an MC gen or in a poly with a gen or however you want to do it. But I'm just going to do it all in here. So I'm going to actually write our own oscillators instead of just do this. And in order to do that, we're going to have to remember the phase and things about each oscillator for each frame. So one way to do that is with buffers. Another way to do that in gen codebox is with a 2D data object. So data it can work very similar to a buffer, and you also peek and poke it. Similar, there's more differences behind the scenes in them. I encourage you to look up what those are. But yeah, so you can think of it kind of like a buffer here, but it is different in ways. So I'm going to do data, I'm going to call it oscillator info. And it's going to be a 2D array or whatever. So we're going to give it the size of 8 because we have 8 particles. Now this is a static number. You can't change that with this thing out here, this number 8, because it's hard-coded, and you can't make this a variable. So if you want to have different particles, I would suggest to write here the maximum value. You know, like if you had up to 13 or 64, you'd type in like 64. But then you have separately the number of particles, and then you just access the amount that you want. So you start with the maximum here, but you don't have to use all of it, depending on your project. But I'm just going to do 8. We'll keep it static. And then I'm going to give it... In the end, we'll need 3, but I'm going to start with 2 other dimensions. And what are those 2 other dimensions? So we know, or well, yeah, what are those other 2? What are the 2 values? So we know we have 8. This creates a 2D array. You might want to look up what those are. So we have 8 particles, and then for each particle, just like the buffer, we have 2 values. The buffer we had 4, but this one we just have 2. What are those? Well, the first one's going to be the phase of the oscillator, and the second one is going to be the phase increment, which is based off the tuning frequency. And I'll kind of explain that as we go. This is basically just the amount that the phase increases each frame, and that relates to like the tuning frequency it's at. Okay, so let's code all that. Now remember what I said earlier, that every time we get a new particle, we want to get a new random tuning for the particle, and it's just going to hold that tuning. So we can do that in the same function, but we need to add another argument. We need to send in the oscillator info. I'll just name them the same to make it easier. Oscillator info. But you don't have to name them the same because this is local to this function. So first I'm going to add that to all of these. So I'm going to add it to this one and to this one. So we're just sending in this data array into this function now for it to be used. And so let's set up the oscillator. So we don't have to set the phase because we can let the phase just be wherever it's at. I don't really care about that. But we do have to get our random frequency. So our frequency is going to be a random number noise, which gives us from negative to 1 to 1. And then I'm going to scale that. This is just like the scale object in normal max. So I'm going to scale the value noise from negative 1 to 1. That's the value it gives you. And I'm going to use MIDI numbers. So let's say a range of 30 to 80 in MIDI terms. So this is, from 0 to 127, but we don't want that full range. We're just going to do from 30 to 80. And then I'm going to do, conveniently, the MIDI to frequency function of that. So this will give us a frequency, a random frequency based off the MIDI values between 30 and 80, which is a good range. Right, and then let's store that in this oscillator info. So osinfo.poke. The first one is the value, so we're going to poke the frequency. But remember, this isn't the frequency itself. This is the phase increment. So to get that phase increment, it's going to be based off the sample rate. So we're going to divide it by the sample rate, and that will give us our appropriate phase increment. And then we're going to store that in the index, just like the other ones. And then the channel is this one offset, just like we said here. So once again, we're getting a random frequency, and we're converting that to a phase increment, which is based on the sample rate. And then we're just storing that in the at the index of the particle and offset in the channel 1 because that's where I'm storing the phase increment at. Cool. Okay, so that will give us a random frequency. Great. So let's actually create that tone. And we need to sum all of those signals and output them too. So we're going to do panning in the end, so we'll do a sum for left and a sum for right, and we're going to initialize them both at 0. And then in the end, we're going to output the first outlet equals sum left, the second outlet equals sum right. So here we're outputting the sum of all these oscillators out left and right. And let's hook those up. So left, and let's create another outlet here for right. Great, so now they're going to output, but we actually got to give them some signals to output. So what is the signal going to be? Well, the signal, let's start with the signal. So this is going to be the signal from the oscillator. And actually, before that, let's get the phase. So we're looping through these, and we need the phase. And the phase, if you remember, is stored in the first channel of this oscillator info thing. So it's going to be osinfo.peak. And we're going to peak the I, because it's the particle we're on, and then the index is 0. So that will give us our current phase. And then, right. And then, so then we want to get a signal, a sine wave signal based on that phase. There's different ways you could do this. An easy way to do it is to use the cycle object still. But you have to say, so usually if you did this, this actually is supposed to be the frequency. But instead we'll say index equals phase. So in Gen codebox, this is how you can give it certain arguments, and I'll explain in a second, or I'll explain now. So let's create a cycle up here just to see. So it says wave frequency, right? But we're giving it the phase instead. And if we say help, it will tell you right here that if the at index or the argument index attribute is set to phase, it can be driven by a phase input instead. And that works very similar to how the tilde cycle out here works, where you see if we go in the right inlet, you can control it by the phase instead of giving it a frequency. So it works just the same. So yeah, that's essentially that's what we're doing here. We're getting a sine wave in a more efficient way. This is more efficient than, say, doing this. You know, you could do this if you want, but this is less efficient because I think the cycle uses a lookup table, maybe an interpolated one. So this is just a more efficient way of getting a sine tone. That's how you have to do it. So now we have the sine signal. Now, before we output and all, we have to increment the phase because it's just staying at 0 right now. So we have to do phase. It's going to be plus equals. So we're going to remember that's just like saying phase equals phase plus something. And what are we going to add it by? Well, remember, we're going to add it by the phase increment that we calculated here based on the frequency. So let's just get that value, osinfo.peak. And it's going to be, again, the index and at 1. Just like we got the phase here, we're getting the phase inc here, so we're just adding it by the phase increment. Great. But we're not done yet. We have a couple more things to do, because once this is just going on forever, which might be all right. Even for a sine function, that might be all right. But we just want to stay it between 0 and 1. So we got to say, a good way to do this is to do a while function. You can also do an if. So let me demonstrate with if first, so it's maybe a little more clear. So if the phase is greater than or equal to 1, because it's just going up like a ramp, then we want to minus equal it by 1. So we don't set just... Sorry, we're going to do phase minus equal 1. So we wouldn't do phase equals 0 because let's say it was like, it's not always going to be perfectly 1, right? And we don't want to like lose some of that frequency. So instead of just equaling it to 0, or we might lose a little bit of the frequency, although give it probably not that much. It might change the frequency a little. We're instead going to minus equal by 1 so it kind of retains that same frequency. And then even, this will probably work fine, but an even safer way is to say while, because like, let's say for some crazy reason the increment was so high it went like way over 1 and it was at like 2 or 3, we have to keep minusing until it gets back to the 0 to 1 range. So while is a safer way to do this. And then there's one last thing we need to do for the phase, and I'm just going to write phase increment here, or phase adjustment maybe. And sorry, I'm just going back. So get signal, get sine wave, signal, phase adjustment, and then the last thing we need to do is store the phase. Otherwise, it's just going to stay at 0. You know, we're getting it here, but we're not poking it back in. So we need to poke it back in. Sorry. Okay, osinfo.poke, and we need to poke what? The value of phase at the index, sample index of I, and at the channel offset of 0. So just to recap, we get the phase here. We get a sine wave based on that phase. We increment the phase based on the frequency. If we go out of bounds, we got to send it back, the ramp back to 0, and then we store the phase so that it actually increments each frame. Great. So what's the final thing? Let's sum it, and later we'll do the wavefolding and panning here. So let's just sum, and I guess we can do the panning now, why not? So let's do linear panning first. Now, remember I said the panning is going to be based off the x value. So just like here, we can get the x value again. But we can actually just call it pan because, you know, we're just going to use it. Now remember, this value is from -1 to 1. I want to get it to 0 to 1. So to do that, I'm going to multiply 0.05 and plus 0.5. So multiply multiplied by 0.5 converts from -1 to 1 to -0.5 to 0.5, and then I just offset it by 0.5, and now I'll change it to 0 to 1. And then so now let's do the panning so with the summing. So here's how we do it. So we get the sum L, which is outputted, and we plus equal. We don't say equal because it'll just keep erasing the value for each particle, setting it again. So we need to sum it based on all of these oscillators. And and then we'll sum it. We're going to sum the signal, but we want to pan it. We're just going to do linear panning, nothing fancy. So to pan it, we'll just get the inverse of the pan for right, because right now the pan's from 0 to 1. So if it's at 0, it's panned left. If it's 1, it's panned to the right. So yeah, here we get the signal, which is from the sine wave, and it's the sum left is the left panning of the signal, the sum right is the right panning of the signal, and then we output those. Great. Now this might get kind of loud because we're like, you know, we're doing 8 particles and summing them. You know, that's a pretty big value. Now, depending on your project, you'll reduce the gain in a lot of ways. I'm going to reduce the gain outside of here. I don't care. But a common thing is if you're doing like an oscillator bank, a common thing is for the voice reduction gain. Voice gain reduction is to be this equation. It'll be 1 divided by the square root of the number of particles or whatever. So for us, that would be 8. That deals like with the correlation. So you might not want to do this. You might want to just do 1 divided by 8 if they're correlated, I believe. But they aren't because they're being panned and wavefolded and stuff. So yeah. Now, I'm not even going to do that here. I would usually, and I would usually not run this function all the time. I'd check if it changed and only update it then and store it in a history value. But I'm just going to keep this simple and just like reduce the gain after the fact out here. So we should be able to get an oscillator bank now that's being panned based on the x position. So let's hear it. I'm going to do a live.gain. Yep, and you can see it's really loud because it's 8 of them. I'm just going to reduce that a bunch. All right, and let's see if it works. Woo! Sorry, I'm getting audio dropouts again. It must be my interface. I'm not sure. Anyway. Great, it works, but you hear there's like a little tiny click. And that's because every time it reaches the outside, it resets the position. But that jump also changes this panning value, and it doesn't like that. It doesn't like just jumping the gain because that causes the sample, the sample value, the gain, the waveform to change quickly. So what we need to do is smooth the panning. Now this isn't a very trivial thing to do in this for loop, just like creating a sine wave oscillator wasn't trivial. So I'm going to actually copy paste in a smoothing function I have. Okay, so I've just copied and pasted over a smoothing function I wrote a while ago and use a lot. I'm not going to really explain it, but this will just smooth the value given a new value, the previous value, and like a smoothing amount. So if we want to do that for panning, we need to remember the previous panning value. So let's just conveniently use our os_info data to remember our last panning value for each particle. So I'm just going to increase the number of values that this has to 3, and that second offset channel is going to be the last panning. All right, so then we can remember that and use that history to smooth the panning for each particle. So, all right, so we get the pan here, right? But we're not just going to straight up store it. We're going to do the smooth value. So we're going to say pan equals this current panning, and then that's going to be the target value. And then we need the previous one, which, like I said, is osInfo.peak I, 2. And just to remember, that's because the 2 offset is the last pan. So this will give us our last pan. I mean, since this is a tutorial, I should just write this out. So last pan equals that. So yeah, we'll do it like this, right? And then I like to use this value for this smoothing function I wrote. It works generally well. Okay, and then we need to actually store this again so it remembers it. So osinfo.poke, and we're going to store the pan for later at the index, sample index of I, and the channel. Sorry, more audio dropouts. Okay, cool. And now, so now we get this smoothed out panning value, so there's no clicks, and then we do the same thing as before. So let's see if there are clicks now. Nope, sounds pretty smooth. So the last thing I wanted to do is to, so now we have the x-axis based off of the we have the panning based off the x position, and I said I wanted to do a little wavefolding thing based off the y. So I just copied over a little wavefolding algorithm, and let's just throw it in here. I already did it before. Let's throw it in before the panning. So I'll just paste it. So yeah, let me give it some space and go through it. So actually we have to do something. We have to get the y value. So it's just going to be like the x. Y equals the particles dot peak, and we need to peak the index we're on to get the current particle, and then the y is at channel offset 1. So right here I'll do the index and 1. So this will give us the y position of the particle, and then I base the wavefolding off. I convert that. Actually, you know what? Maybe I'll do it just like the panning, a little cleaner. I'll get rid of this y variable altogether, and just here's the y, and then I convert it from -1 to 1, just like I did with the x, by multiplying by 0.5 and offsetting it. So this is just getting a value that's going from 0 to 1 based off the y value, and that's our wavefold amount. And then there's just like some gain reduction stuff here that I made based off the wavefolding. It's just like something I dialed in. And then the wave gain itself is for the wavefolding to happen. This is something I got off. I can't remember the source of it. Just a really simple wavefolding algorithm here. So remember, sig is our sine wave. And so here we're wavefolding that sine wave based on the y value. Can't tell you I know the math behind this well, so I'm sorry to disappoint you there, but it should work. So basically we'll get this wavefolding amount from 0 to 100% based on the y value, and then fold the sine wave. So let's hear how that sounds. Hopefully it works. Seems to work. Let me lower this to 1 particle. Okay, sorry, there's an issue doing the 1 particle, and it's because I have to kind of decouple a couple of these things so I don't hit the reset and reset it back to 8. So I'm going to do a separate number box that we can just adjust. And we can only do up to 8 because of how I set up the oscillator data object. So yeah, let me move these around. Okay, cool. So now I should be able to move this down to 1. Okay. Sorry, keep getting audio dropouts. I think because the video's recording. I don't know why I am, honestly. The CPU is very low. It's not that. But yeah, hopefully you can hear and see that the Y is indeed controlling the amount of wavefolding and X the amount of panning. So I'm just gonna expose this velocity scaler so we can change the speed a bit, and then play around a little so you can see the fruits of our efforts. Yeah, I mean, there's a little rough messing around, but hopefully you get it. Yeah, as you saw, maybe a better thing to mess around than this scaler would be like if I, instead of had this frame rate at a fixed 500, maybe make that, a frame rate parameter, and then instead of controlling the velocity scaler, maybe I would just control the frame rate. I mean, we can try that real quick. Frame rate, and let me reset it. All right, and then this should scale the speed a little better. Cool, yeah, the frame rate works a little bit better, but hopefully you can understand how those are interconnected. Okay, so that kind of ends our demonstration. Let me make a few notes about recapping stuff and where to go from here, etc. So just to recap, we've created a very simple particle system that controls an oscillator bank, the oscillator bank's wavefolding and panning. We're centralizing all this using this buffer particles data object so that we can access the position and other info about the particles we want to expose in all kinds of places. Now, right now we're just accessing them in this visualizer here of OpenGL, and in Gen codebox. But let's say we had a JS UI or JS or some other stuff. You could also access the same buffer in there, so it's pretty convenient. No need to like send things everywhere. You can just keep accessing everything in this central buffer. Yeah, where to go from here? Well, it depends on what aspect. Obviously the particle system, you could do a lot more cool stuff, add gravity and add other forces, control many other kinds of things, maybe not even do like some particle like this. It could be all kinds of stuff. This doesn't have to be particles. This could be like any kind of iterative multiple object thing that you could do this in. You can also use this. I don't know if this is the most efficient thing, but sometimes I do it. Is you can just also use the buffers for parameters themselves. So if you had like B patchers with many, like let's say you had like 8 different oscillator systems and each of them had their own B patchers, you could have a single buffer in which the parameters of each of those 8 things or whatever amount are stored in different channels of the buffer or whatever. It's just the buffer really opens up, when used as a data object, this kind of convenient access, all kinds of. Sorry about that. Just offers a really convenient access in many areas of Max. And you can use it in so many ways. So I just wanted this demonstration, this is some kind of system or systems like this I use a lot in my devices. Not even in just this way with particles, like I'm saying in all kinds of other ways. And this is hopefully this demonstration gives you a little bit of an idea how to do that, and like all kinds of ways you could do that. And hopefully along the way you learn some other cool tricks in codebox and DSP in general. So yeah, I hope this was helpful. And yeah, have a good day.